Hello everyone. So today I'm going to explain equations reducible to exactness. If you remember vividly, I've explained what exactness of a differential equation is. So today there are some differential equations that are not exact. Now, how do we go about them? We have four different rules in solving this type of differential equation. Now, look at rule 1. In rule 1, when you have partial m over partial y minus partial n over partial s all over n, when you are using this first rule, it must be a function of s. It must be what? A function of s. Now, let's solve this example to show if this rule will work for it or not. Now, we are given a differential equation. Don't forget, from our previous class, this is denoted as our m, while the whole of this is denoted as our n. Now, let's find our partial m divided by our partial y. Will it be equal to partial n all over partial s? Now, let's try that. Now, what is our partial m divided by partial y? Now, let's differentiate m here with respect to y. If you differentiate this y, we have 1. If you differentiate this, we have plus 1 over 3 y 3 minus 1. And this is not, there is no y here. So we have our 1 plus y, yes, y raised to power 2. So if we differentiate m with respect to y, we have 1 plus y squared. So here will be 1 plus y squared. Now, for the second one, when you differentiate n with respect to s, that means we are differentiating this with respect to s. Now, our partial n to partial s. Now, let's differentiate this. If you differentiate this, we have 1 all over 4. That means if you differentiate 1 all over 4s. Now, if you differentiate the second one, we are going to have, if you differentiate this, the s here, we have 1. So we have plus 1 all over 4 y squared. So as you can see, 1 all over 4 plus 1 all over 4 y squared. There is not what? It's not exact. It's not what? It's not exact. So which implies that we need to test for this rule 1 if it will work for the differential equation or not. Now, since they are not exact, then we have our partial m over partial y minus partial n over partial s all over n. Now, let's substitute our values. What's our partial m over partial y? Partial m over partial y is 1 plus y squared. So we have 1 plus y squared minus partial n over partial s. Partial n over partial s, 1 all over 4 plus 1 all over 4 y squared. 1 all over 4 plus 1 all over 4 y squared all over n. And our n is the whole of this. 1 all over 4s plus 1 all over 4 sy squared. So this is what we have. Now, let us expand. From the numerator, we have 1 plus y squared minus 1 all over 4 minus 1 all over 4 y squared all over 1 over 4s plus 1 all over 4 sy squared. So from what we have here, if you look at this, 1 minus 1 over 4 will be 3 all over 4. Y squared minus 1 all over 4 y squared. This implies that we have 1 here. So we are going to have plus 3 all over 4 y squared all over 1 over 4 s, or let me do it like this. 1 over 4 s is common to both. So we have 1 over 4 s. We are left with what here? 1 plus y squared. And if you look at the numerator as well, we have 3 all over 4 is common. Then we have 1 plus y squared all over 1 all over 4s, 1 plus y squared. So this and this will cancel out. So we are left, so look at this very well. We are left with 3 all over 4 divided by 1 all over 4s. So this will be 3 all over 4 multiplied by 4 all over s. So 4 will cancel out 4. We are left with 3 all over s. So 3 all over s is the value we got for the first one. Because this is 3 all over s, 3 all over s is a function of s. So we are going to use this particular rule to solve the problem. Now, after getting this, we need to get our integrating factor. So I'm sorry, this will be a bit long. It will be a bit long. So let's get our integrating factor. Our integrating factor will now be exponential. Let me write my integrating factor here. Okay. Our integrating factor will be exponential integral of f of s ds. Which exponential, what's our f of s? 3 all over s. The value we got here, which is 3 all over s, will be our f of s. So we have 3 all over s ds. And that will give us what? Exponential 3 integral of 1 all over s ds. So exponential 3 ln of x. So this can also be written as exponential ln s raised to power 3. So exponential and ln will cancel out. We'll be left with s cubed. So our integrating factor is s cubed. Our integrating factor is what? S cubed. Now, after getting the s cubed, what are we going to do? So we are going to use the integrating factor s cubed to divide each of the term that we have here. Each of the term that we have here. So the integrating factor you are going to get will be used to what? To divide all the values that we have here. Are you getting my point? So now this is the question itself. Let me call the question equation 1. The question as equation 1. Equation 1. So we are going to use this integrating factor s to what? To multiply each of the value that we have here. I think initially I said divide. You are going to use this to what? To multiply each value that we have here. So look at this. This will give us s cube y plus 1 over 3 s cube y cube plus 1 all over 2 x raised to power 5 all the s plus 1 all over 4 s cube will be x raised to power 4, because when s cube multiply this, it will give us x raised to power 4 plus 1 all over 4 s cube, this x cube s1 x raised to power 4 y square all the y. Now, what I'm saying now is, after multiplying by the integrating factor s cube, I multiply this by s cube, s cube, s cube, s cube, s cube. So I obtain all this. Now, after multiplying by the integrating factor s cube, then the equation will be exact. Now, let me demonstrate that to you guys. Now, what is our partial m to partial y? Let's look at it. If you differentiate this with respect to y, we are going to have s cube. With respect to y here, yes, we are going to have 3, we cancel out 3. We are going to have s cube y squared plus s cube y squared. If you differentiate this with respect to y, there is no y here, so we don't differentiate this. Now, so we got s cube plus s cube y. Now, let me check the second one. Partial n over partial s. So, let's differentiate this with respect to s. If you differentiate this, we are going to have s cube. If you differentiate this, if you differentiate this with respect to s, we are going to have 1 over 4 s cube y squared. So this will cancel out this. We have s cube plus s cube y squared. So which is the same thing with this. You can see they are exact now, right? And from our previous class, I said when a differential equation is exact, what are we going to do? It's very straightforward. The fact that this differential equation is exact, the next step is to find our integral of m ds plus the integral of n without s equal to a constant. Now, how do we go about that? Now, let's integrate the whole of this with respect to s. If you integrate this, you have x for all over 4 y. So we are able to integrate this. We have what? S for all over 4 y. Plus, let's integrate this with respect to s. No, I'm integrating, yes. S3 plus 1 all over 4, yes, is correct. And if we integrate this with respect to s, we have 1 all over 3 s for all over 4. So which is s raised to power 4 divided by 12. S raised to power 4 divided by 12 with y cube. Now, we integrate this with respect to s as well. We have half s6 all over 6. So this will be s raised to power 6 divided by 12. 2 times 6 is 12. So we have s raised to power 6 divided by 12. So we are done integrating this. Now, this one, let us integrate this without s. That means any of the values with s will be nullified. So this one, there is s here. This one, there is s here. So we don't need to integrate any. So this is our answer, and this will be equal to what? C, a constant. So this is our answer for this equation reducible to what? To exactness. The procedure of solving this method is to make sure you test for all the rules. We have 4 rules. One of the rules, the first one that I did here, must be a function of what? A function of s. Which I said our partial m divided by partial y minus partial n divided by partial s all over n must be a function of s. And at the end of the day, we're able to get our 3 divided by s. So this 3 divided by s, the integrating factor is what? Is found where we obtain our s cube. So the s cube is used to divide each of the values that we have in this differential equation, and we are able to get our answer. Thank you. Another example on the first rule of equation reducible to exactness. So the same procedure. This is our m and this is our n. So our partial m to partial y, if we differentiate this with respect to y, we have 1. And if you look at this, if you differentiate this, partial n with respect to y, what are we going to get? So this one is, I want to expand this. We have minus s plus x squared y. So with respect to y here, with respect to y, we are going to have plus, I want to differentiate this. Oh, I'm sorry, with respect to s. Sorry, I'm confused. If we differentiate this with respect to s, we have minus 1 plus 2sy. We differentiate this with partially with respect to what? With respect to s. If we differentiate this, we have what? Minus 1, and this is 2sy. So if you look at this and this, partial m to partial y is not the same thing as what? Partial m to partial s. So they are not exact. So according to our rule 1, we have partial m, partial y minus partial n over partial s all over n. So let's use this to show if it's a function of s. So we have this to be 1 minus 1 plus 2sy all over, what is the value of our n? Minus s plus x squared y. So let's keep solving. So this will give us 1 plus 1 minus 2sy all over. So s is common to this. So we have s. I can say minus s is common. Let me say minus s. So we have here to be 1. And that will be what? Minus sy. I can put it like this. Yes. And if you look at the numerator, 1 plus 1 is 2. So we have 2 minus 2sy all over minus s, 1 minus sy. So I'm bringing this down here. So we have 2 is common to the numerator. We have 1 minus sy all over minus s, 1 minus sy. So this, we cancel out this. So we are able to get what? We got 2 minus s. Now, after getting this, we need to get our integrating factor. And what's our integrating factor? Our integrating factor will be exponential integral of what? Minus 2 all over s, all the s. So 2 is a constant, minus 2 will come 1 minus s ds. That will be a minus 2 ln x. So minus 2 will come here. So we have exponential ln s raised to power minus 2. So this will cancel out this. We are left with s raised to power minus 2 or 1 all over s squared. So our integrating factor is what? 1 all over s squared. 1 all over s squared. That's our integrating factor. So our integrating factor is 1 all over s squared. So I hope you understand what I did. What I did is very straightforward. Partial m, partial y is not equal. They are not exact. So what I did is to use the first rule. And the first rule states that partial m, partial y minus partial n, partial s all over what? N. So I make my substitution. Partial my is 1 minus the whole of this. Partial ns is this all over n. So I collected like terms. Then I got 2 minus 2 over s. After getting this minus 2 over s, I need to find my integrating factor. And to get integrating factor, it is always exponential integral of the value that we got. So after solving this, we are able to get 1 all over x squared as our integrating factor. And after getting our integrating factor, the next thing is to use the integrating factor to multiply each term that we have here. So at the end of the day, we have, let me write it out, y minus, so it will be 1 all over x squared times y. For this, minus 1 all over x squared times 2x cubed. So that is our ds. Minus, we have our minus s divided by x squared plus x squared y all over x squared, all what? The y. It's right. This one is minus x plus x squared if I expand it. So this should be minus. If I expand this, I will get the same thing. Now, so at the end of the day, this will be y all over x squared minus this. We cancel out this. We have 2s, all the s, and this will be 1 all over s minus y, all the y. Now, if you look at this very well, if you find your partial m to partial y, it must be equal to partial n to partial s. Now, when you differentiate this with respect to y, we are going to have 1s squared. If we differentiate this with respect to s, you are going to have 1x squared. So which is exact. So if this one will later give us minus 1 all over x squared if you differentiate, but because of this negative sign, it will be positive. So that is why we have this. So it is exact. So since this is exact, now the next thing is what? To integrate m with respect to what? To s, plus n without s, all equal to a constant. Now, if we integrate this at the end of the day, if we integrate this with respect to s, just neglect the y. The y is constant. So we'll be left with 1 all over what? 1 all over s squared. So we are supposed to integrate this. If we integrate this, we have x raised to power minus 2, right? Plus 1 all over minus 1. So at the end of the day, the whole of this will give us x raised to power what? Minus 1. Because we have negative here, so minus 1 all over s. But because of this y, it's a constant, so we have the first one here to be minus y all over s. This negative, if we integrate this with respect to s, we have minus 2x2 all over 2. So 2 we cancel out 2. Let me leave it first. Plus, let us integrate this without s. So we are not going to integrate this because there is s here. We are left with just y. If we integrate this, we have what? We have minus and minus is plus, so it will be plus. We have y squared all over 2 equals c. Now let me rewrite the whole question. Now, so this can also be written as, yes, minus y all over s. 2 we cancel out 2, minus s squared plus y squared all over 2, all equals c. So this is our final. That's our what? That's our final answer. So this is second rule on equation reducible to exactness. Now, how do we make use of this rule? This second rule must be a function of y, while the first rule must be a function of s. Now we have this, and we want to solve this example. Now the first thing we are going to do is to show if they are exact or not. So let's find our partial m to partial y. If we do that, if you differentiate this with respect to y, we have 12x squared y cubed. Plus, if we differentiate it with respect to y, we have just 2s. Now, partial n to partial s. Now let's differentiate this partially with respect to s. So we are going to have 6s squared y cubed minus 2s. Now you can see they are not exact. So we need to use this rule too. Though when you are writing the exam, you will not be, the rule that you are going to use will not be stated. But for better explanation, I'm just trying to solve the rules and the examples side by side. Now, since they are not exact, then we apply this rule. Because I know at the end of the day it will be a function of y. So this will now be partial n to partial s minus partial m to partial y, all divided by m. So partial n to s is 6s squared y cubed minus 2s. This negative sign minus the whole of this. It will be 12x squared y cubed minus 2s, all divided by m. And our m is what? Our m is 3s squared y raised to the power 4 plus 2sy. Now, since we have all this, let us bring all the like terms together. I will need to manage this point here. I will need to manage this board. So let's look at this very well. This and this are the same, and this and this are almost the same. So this is half of this. So at the end of the day, 6x squared y cubed minus 12x squared y cubed. So if we subtract this from this, we are going to have minus 6s squared y cubed minus 2s minus 2s will give us minus 4s divided by the whole of this. Now something is common to this and this. What is common to this and this? S and y. Sy. So sy is common. Then if sy is common here, we are going to have 3s left. Yes, 3s plus sy is common. Sy we are left with 2. So let's look at the numerator as well. 2s is common. So we have 2s for the numerator. We have 3 left here. 3sy cubed. Yeah. 3sy cubed minus, let me put minus here, and this will be plus, and we have just 2 here. I think I made a mistake here. I said here should be y cubed. So here will be y cubed. Here will be y cubed divided by sy 3xy cubed plus 2. So this will cancel out this. We are left with s will cancel this. We are left with minus 2 all over y. We are left with what? Minus 2 all over y. So since this is a function of y, then using this second rule is the right one. Now, this is not where you are going to stop. After getting your value here, you need to find your integrating factor. And how do you get your integrating factor? Getting integrating factor, IF, integrating factor. Our integrating factor will now be equal to exponential integral of minus 2 all over y, all the y. So if we integrate this with respect to the exponential, we are going to get minus y raised to power minus 2. So if we integrate this, we are going to get our integrating factor to be 1 all over y squared. So if you check the first rule, I've explained how to integrate something like this. How do you integrate this? Minus 2 is constant. You bring minus 2 outside the integral sign. So we'll be left with 1 over y. So that will be minus 2 ln y, or minus 2 log y. So exponential will cancel log, and you'll be left with y raised to power what? Y raised to power minus 2. So we got this. So our integrating factor is what? 1 all over y squared. Now, since our integrating factor is 1 all over y squared, as I said earlier, we are going to use the integrating factor to multiply each of these terms that we have in the question. So let me call this equation 1. Now, how do we do that? So let's divide the whole of this by y squared. So we have 3x squared y raised to power 4 divided by y squared plus 2sy divided by y squared, all the y, plus we have 2s cubed y cubed, 2s cubed y cubed divided by y squared. It's not divided, we are multiplying by 1 all over y squared minus s squared all over y squared, all equal to 0. Don't forget, we multiply by 1 all over y squared. We multiply each term. We multiply each term by 1 all over y squared. So that's why we are able to get this. We are not dividing, we are multiplying. So if you check this very well, this will give us 3x squared y squared plus this will be 2x all over y all the y plus this will give us 2x cubed y minus x squared y squared, all equal to 0. So if you check partial m to s, it must be equal to partial n to y. Let's check it. If you differentiate this with respect to s, we are going to have 6s y squared. If you differentiate this with respect to s here, this is a constant, we are going to have s. So we have plus s all over y. Now let's differentiate this with respect to, this one with respect to s. Yes, I'm right. Partial m to s. And if you differentiate this with respect to y, we are going to have, if you differentiate this with respect to y, n with respect to y, 6x squared y. Let me check this properly. Yes. If you differentiate this with respect to s, 1 minute. So this is s. This is partial s. This is partial s, partial s. This is partial y, partial y. So I will differentiate my m with respect to y and n with respect to s. So if you check m with respect to y here, we are going to have 6x squared y. With respect to y here, this is a constant. If you differentiate 1 over y, we are going to have minus 1 over y squared. So this will be minus 2x all over y squared. Now let's differentiate this with respect to s. If you differentiate this with respect to s, we are going to have 6x squared y. Why if you differentiate this with respect to s, the same thing, we are going to have minus 2s all over y squared. So this is n with respect to s, and this is m with respect to y. They are the same. 6x squared y minus 2x all over y squared, and this, they are the same. So since they are exact, the next step now is to use our normal procedure for exactness. And what's our normal procedure? Integral of m, the s, plus integral of n without s equal to a constant. Now let us integrate this with respect to s and integrate this with respect to what? With respect to y. But if any term with s will not be integrated. That's why I use n without s. Now let's integrate this with respect to s. If we integrate this with respect to s, we have 3x cubed all over 3y squared. So 3 will cancel out. We are left with s cubed y squared. For this, s cubed y squared. Now let's integrate this with respect to s. This y is constant. We have integral of 1 all over y to s. So if we integrate this, we have 1 over y 2x squared all over 2. 2 will cancel out 2. So we are left with x squared all over y. So the integral of this is plus x squared all over y. Now, once we integrate this n without x, there is s here, so we can't integrate this. There is s here as well, we can't integrate this. So this is nullified. So at the end of the day, this is our answer. This will be equal to c, where c is constant. So this is our final answer. Now, let me solve another example on the second rule. Now, we have our partial m to partial y. So let's differentiate this with respect to y. We have 3x y squared and this to be plus 1. Now, partial n with respect to s. With respect to where we have 4s y squared plus 2 to respect to what? Respect to s. So we have this. They are not exact. Now, since they are not exact, we know what to do. Partial n to partial s minus partial m to y all over m. So n is what? Partial n is 4xy squared plus 2 minus 3xy squared. After expanding, this will be minus as well, minus 1 all over m. M is sy cubed plus y. So if you look at this, they are the same. So it means 4 minus 3 is 1. So we have sy squared plus 2 minus 1 is what? Plus 1 all over. What is common to this and this? Y is common. So we are left with sy squared plus 1. So this will cancel out this. X squared, yes, plus 1. We have this. We have, let me get it right. Where is my pinner? So we have this. Let me write it properly. So let me put somewhere here. So we have this 4 and this will give us sy squared plus 1. And we have, what is common to this and this? We have y is common. Then we have sy squared plus 1. So this and this are the same. We can cancel out. So we are left with 1 all over y. 1 all over y. So after getting our y all over y, 1 over y. So 1 over y is a function of what? Function of y. So this is what? Is valid. So we need to get our integrating factor. So what's our integrating factor? Our integrating factor is exponential integral of what? 1 all over y. So that will give us what? Exponential ln what? Ln x. Ln y, sorry. Ln y. So at the end of the day, we have y as our integrating factor. We have y as our integrating factor. So if y is our integrating factor, we are going to use this integrating factor to multiply each of these terms that we have, each multiplied by y. So let's multiply our value. By multiplying, this will be xy raised to power 4, y squared, and so on. So let's multiply. We have sy raised to power 4 plus y squared all the s plus multiply this by y, 2x squared y cube, 2x squared y cube, and this be 2xy plus 2y raised to power 5 all equal to 0. Now if you look at this, if you differentiate partial m to partial y, it must be equal to partial n to partial s. M to y, if you differentiate this, we have what? 4xy cube plus 2y. Now n with respect to s, we have 4sy cube. With respect to s, we have 2y plus 2y. So no s here. So you can see they are exact. So if they are exact, we know our final answer. Our final answer will now be integral of m dx plus integral of n without s. Now if you integrate this with respect to s, here we have x squared all over what? 2. But because of the y, you can say y raised to power 4 plus with respect to s. So this implies that we have y squared ds. That is the meaning of this. So y squared is constant. We have integral of ds. And integral of ds is s. So we have y squared s. Or we can say xy squared. So this will be plus sy squared. Plus, let's integrate this without s. So there is s here, we nullify. There is s here, we nullify. So we have 2y raised to power 5. So that will give us what? 2y6 all over 6. So at the end of the day, we can write our answer as x squared y4 divided by 2 plus sy squared plus this we divide by this, we have 1/3 y6 all equal to c. So this is our final answer. So we have 4 rules in solving equation reducible to exactness. So we've done 2. In the following class, we are going to solve additional 2 rules we use in solving this type of problem. Thank you.